So usually when we're talking about chemistry, we're talking about galvanic or voltaic cells, which are spontaneous and they generate electricity much like, so examples of these would be a battery or a fuel cell. So we have some special notation for writing these guys. So you start with the anode, and so you have the electrode on the far left side, and then you have a phase bound, so you cadmium, solid cadmium, and then you have a phase boundary, which is a single vertical line, and then you have cadmium nitrate as an aqueous solution. So you're talking about the, let's see. So all right, and then you can have a salt bridge, which maintains electroneutrality as you're having electrons go around through a voltmeter or through a circuit, and then you have, so that's a double vertical line. Then you have your cathode, where you have maybe your aqueous species, and then your cathode electrodes. So you have electrodes on either end, and then aqueous species in the middle. And so every time you have different phases, you separate them by a single vertical line for a phase boundary, and in between the anode and the cathode side, you would have a salt bridge. So, let's see. So you can draw that. From this information, you can draw this. So you have the cadmium electrode over here, your anode, and then you have electrons going through the voltmeter onto the cathode side. You have the cadmium in solution. And then you have, because you're having electrons, negative charges going out through the wire, you have the nitrate in the salt bridge moving towards the cadmium nitrate side. So then, as you get over here, you have silver as your cathode electrode, and your silver nitrate in solution. And since you're having electrons coming in here, you also have a higher concentration of potassium right over here in your salt bridge. And that's how that works. So that was a lot of information. We're going to get a lot of practice writing cells in that notation. So if you look a little bit, you can also write what's going on as half reactions. So here's what you had going on your anode side, where you have copper or cadmium solid dissolving to cadmium 2+ and creating 2 electrons. And that has an E0 associated with it. You can also have, if you added 2 electrons to this side, you would have 2, so you have these 2 electrons coming over here, and then you have 2 silver ions plating out as silver on the cathode electrode. So then you can add these together, and you have to do that with the same number of electrons in each, so you have to cancel your electrons. So you have cadmium solid plus Ag2+, or Ag plus and 2 Ag plus in solution goes to cadmium 2+ plus 2 solid silvers. And you can calculate your E0 for that. It's E0 equals E0 positive minus E0 negative. So E0 equals 0.799 minus a negative 0.402. So you get an E0 total of 1.20 volts. And remember this 0 we talked about, delta G 0? That means that the activities are all equal to 1 in the solution for all of the aqueous and gas species. So how do we measure these the electrons, the electronic potential of these half reactions? Well, it's sort of arbitrary. We decided that somebody a long time ago decided that everything would be referenced relative to the standard hydrogen electrode, which basically takes aqueous H+ with an activity of 1 plus E- goes to half an H2+ gas with an activity of 1 in the gas phase. So that's defined, that has an E0 that's defined as being 0. And so you hook up you have half of your cell being this the She electrode, and then you hook up the other half and you see which way the electrons run, and then you can assign a potential difference between them. And since this is 0, then you have a potential difference measured for these other reactions. For example, these are always, by the way, these are always written as reduction reactions, and so if you flip it around, you can just flip the sign on the E0. And that's all for the beginning of half reactions. and standard potentials.